try sharing your screen?
Yes. Let me do it.
Perfect.
Okay.
Okay, great.
Yeah, it should have works.
Perfect, and I can hear you fine. So I'm recording the lectures, and I'll post it on the class website as well. So I'm happy to send you a link if you want to use it for anything.
Okay, sure.
Great, and I'll be on most of the time, but I might have to step out to do a few things, but I'll be in and out. But if you need anything, just message me here on Zoom, or just, you can say something. Okay, we have a few minutes. Let's see. I guess I should. Okay, we should start in a minute or so. Are there any questions while we're waiting so far? Feel free to ask. I'm going to start with a few announcements first. So let me share my screen. Okay, let's see. So the first announcement is on Thursday, we'll have a special class where we're going to be doing something called the business model canvas. So for that, you need to watch the video lectures beforehand. And the instructions are here, as you can see on the website. And in order to watch these lectures, you have to sign up for a free account on Udacity, where there's a link here. And then you search for a class called How to Build a Startup. And then you will access the class. And then I want you to watch the first 1, 2, and 3 lectures. So they're relatively short. Definitely the lecture 1, but lectures 2 and 3 if you have the time. And I will make an announcement of this on Canvas as well. You should come having watched this lecture to the class, because at the class we will be we will be doing an exercise called the business model canvas. And it'll be more efficient if you actually watch it beforehand. Okay, so that's the main announcement. And today I'm excited to have Dr. Rujun Sun, who is a scientist with Dr. Scarpulla's, Professor Scarpulla's group. And she will be doing a guest lecture on essentially the physics of solar cells, so physics and material science, because as Dr. Sun said, is a material scientist. So Rujun, go ahead and share your screen. And as always, the lecture will be recorded and will be posted. And if you have any questions, you can certainly shout, you can chat, shout, so I can hear you, or Rujun can hear you. And also, of course, message on Slack as well, as everyone knows by now. Okay, Rujun, the floor is yours. And thank you.
Hey, so thanks, Professor, for the introduction. So can we start? I think yes.
Yes, go ahead. Yeah.
Okay. Okay. So hello everyone. I'm Rujun Sun, a postdoc working with Mike Scopula. So today I will give you a brief introduction about the photovoltaic. So basically, we will focus on the following question. What is photovoltaic? What's the current state of photovoltaic market? The capacity, the price, and the efficiency, and then go to how the solar cell works and what kind of material for solar cells there are, and some advanced technique for further enhance the efficiency. So first, photovoltaic, we call it solar cell. It's a device that converts the light into electricity. Basically, it converts the sunlight into electricity. So it's like you have a tree, and every year you will harvest, for example, apple, peach, something like this for solar cell. You put there, and they will give you electricity, and basically it's current and voltage. You can use it to your facility. It's a very giant semiconductor diode, pn-junction. But before we go to too much detail, let's give a big picture of the PV. So solar energy is a giant container for energy. The motivation for it is about 1970s, and more recently we care about the climate change while we use the energy from oil, coal, and gas. So we pay attention and turn to the PV. So the PV, it's if we use the PV, we can extract it energy and supply all of our power demands actually, but now we don't have installed that much. So we have great potential for it. I have learned that you guys have some basic knowledge about the solar irradiation spectrum and it changes with weather, landscape, altitude, something like this. So that's good. So here is a map about photovoltaic potential. Actually, it's an integration of solar energy you can receive to in a unit of a day and a year. So different places have different sources. So we can take an average value to do some simple calculation to make you have a direct feeling what it looks like. So let's pick this average. So the unit is kilowatt hour per kilowatt picowatt. It means, okay, if you install 1 kilo PV for 1 day, it will give you 5, let's in this way. It give you 5 kilowatts hour electricity for 1 year, it's about 1,800. It's a fair value among the world. So currently, among all kinds of company, about 500 gigawatts have installed until 2018. So if we use this value for year total electricity we can produce, so time them together, you will get a 1 kilowatt hour. What kind of this number is? So let's look at the electricity we get from all kinds of source: coal, gas, oil, nuclear, hydrogen, wind, solar, and others. So it's about, if we collect hydrogen, wind, solar, and other renewable energy, we call it clean energy. So the percentage in 2018 for the global of it's about 37, so 1/3 of it. Among them, the solar, it's about 3.7%. So it's a huge, I think it's a huge number, and the percentage of it will increases in this year, next year, in next 10 years. So we still have a lot of room to install lots of PV. So the PV, where do they use? They mostly we use PV to produce electricity. So we have a huge plant, something called megawatts. But among our life, we also can see a lot of PV on the roof or in some vehicle, car, and the space use a lot of them. You can see if you take a close look. So this depends on what do you want from the solar cell. It has a wide application. So as a unit, it's a solar panel, or we call it solar module. So this one I show here is cadmium telluride. It's we can get the value from the vendor, the area of this panel, and the efficiency, conversion efficiency, and it will test on the standard condition is 1 kilowatts per centimeter square. So it means, okay, this panel can give you 450 watts. If you install it on your roof, it will give you about 2.25 kilowatts hour per day. So imagine how many electrical facility do you have, and how much electricity you will consume. So you can, someone install the roof with a lot of PV panels, so they can supply themselves. They also can produce the electricity to sell it to grid. Then they can earn money. For the market, currently, it's about crystalline silicon and C-film silicon. No, C-film PV. Basically, there is a figure. It says from year to year, the increasing PV module production per year is installed, and the percentage from monocrystal silicon, multicrystal silicon, and the C-film. So the C-film has about 8 to 10%. I mean, very constantly rate, but it's also changed. The monocrystal silicon, the percentage increases in recent year. And among the C-film, technique is composed by cadmium telluride, CRGS, and amorphous silicon. So you see as the year comes about two components, cadmium telluride and CRGS. The amorphous silicon almost, becomes smaller percentage versus year. So this is our current state, what kind of material and PV it takes in our installed 500 gigawatts. We also cares about price. So this chart will show you the module price versus cumulative production in gigawatts scale. So the top right line is about the silicon. So the silicon, you see the price drops a lot. At the beginning, it's about 13. The euro is almost $1, $13, and now it's about 0.25 or 22 cents. It's a lot of drop, right? This because the cumulative production, and for C-film photovoltaic, it's also follow this norm. So now currently and today, the C-film PV, the price is still a little higher than crystal, but as you can imagine, when the installed scale, for example, it's double or triple, it will reduce. But for silicon, it's harder to double. It's already 500 or 600 gigawatts. For 1 year, it just increased a little. So we can imagine in the future, next 5 years, the C-film PV, the price will lower than the crystalline silicon. So we can say, so the total PV system, the cost is not only the module, but also the inverters, cabling, mounting structure, and some neighbor tax cell. So there is a map in 2080. It's about a different scale, and you have different cost for a PV system. We might install residential PV. It's about install it on your roof. So it's about $2.7 per peak watt. So it means it's still expensive. If you see what's your cost for residential electricity for 1 kilowatt hour, something you can calculate. And among them, we can also see the soft cost, means other things. It consists of about 15%. So it's this one is variable. It can change among different countries. For example, in China, it might not that expensive. So the PV module, it's only consists of maybe 20 to 30% of the cost. We have reduced the cost a lot. So that's how you can afford it. So imagine how many roof area you have, or if you have a farm where you install it for investment, you can calculate the input cost and the output cost, output profit it can obtain for 1 year or 10 years, 20 years, something like this. I think in our life, lots of people would like to try this. Maybe not just make profits, it's an advanced concept for healthy life, something like this. So the efficiency limit, we can, for no matter what kind of material, it's a semiconductor, it's a single junction. So the top limit it's about 33%. We can have some advanced technique to improve, but it's almost can only double the efficiency. For commercial module, if you want to open a company to produce module, so the start point is 12%. For some new technology, it's a baby, right? And it will increase and increase. For currently crystalline and the thin film PV, it's about 17, 18 or 20, even higher. So that's the one we can get from the module we have. Here is a map about the history of a solar cell. We have a lot of kind of solar cell we developed. Some have 14 or 15 years. And the efficiency will improve step by step. The highest one is 47. It's a multi-junction and a concentrator solar cell. It's not for our lifetime. It's for space application. Most of solar cells, if you see, this is a lab efficiency. It means the solar cell, the area of solar cell is very small, maybe 1 centimeter square. So this is it's always higher than the commercial module we have. Some emerging solar cell for recent year, the most important thing you can see is Perovskites is less than 10 years and it reached the efficiency almost the same or even higher than cadmium telluride and the silicon or GaAs, which developed for 14 years. So this is an exciting material. A lot of people investigate it right now. So next we will focus about the basic physics of solar cell, or consists of solar cell. So solar cell deals with the solar radiation spectrum and the electricity we can get. So this is a solar radiation spectrum. Most of our light intensity are visible light, I mean from 400 to 700 nanometer. So we need to convert as much as we can into electricity. So for semiconductor, look on the bottom image, we have a valence band and conduction band. The band gap can change for different material due to the different material. So semiconductor, it means it can convert light energy into electricity. So if we absorb one photon, it means excite the electron in the valence band into conduction band. This means convert photon energy into chemical potential or electrical potential. So it's an energy transfer. So we assume one photon produce one electron in conduction band, and below the band gap, we cannot use these photons. So there is a calculation about band gap versus current, maximum current we can get, and the maximum potential means voltage we can get. People can calculate it. So it's a function of band gap. So the DSC means current decreases with band gap, VOC increases with band gap, and the efficiency can be calculated at this code. So it means you can test if a material can be used for solar cell. The optimal band gap should be between 1.0 to 1.5. something in this range, so it can have highest serial efficiency. This map shows current material we developed and its limit, how much it can reach. For example, this is below 15% efficiency it can obtain, then the limit, then the upper limit. We have some excellent solar cell like silicon, gallium arsenide. It's almost approach to the limit. So more efforts, more investigation we have, we can push this efficiency to the limit. That's research in university and the institute do. So the basic thing about the solar cell is the pn-junction, is a p-type material and n-type material. We can demonstrate use silicon, it's classical semiconductor, very standard. So silicon cannot, if no impurity in there, it's insulator. If we dope with some shallow donor and acceptor, it can give us electron conductivity or hole conductivity. So we can change the property by doping. If a p-type material and n-type contact together, the holes in the p-type will recombine with electrons in the n-type. Then they will form a built-in electric field, which will prevent the holes to further do such recombination. The band diagram shows in the right figure. So the potential differential is an energy differential. So if we have a free electron and holes in the space charge region, means there is no free electron hole and there are electric field. If we inject an electron in this region, so under the driving of electric field, electron will diffuse in this way, holes will diffuse in this way, we'll separate it. There is a force automatically. This is a schematic image about C-film solar cell. It's a CIGS or CZTS solar cell. We have P-type absorber and the N-type and the transparent conducting oxide. So when the sunlight hits the solar cell, it will penetrate and the material will absorb it, right? And when the light hits the junction, it will excite electron hole pairs, and these electron hole pairs in the region of junction, they will separated by the electric field, and then if we connect it to a load, then it will have current go through it and have some voltage potential. So there are 3 steps to produce electricity. First, absorb the light, which will generate a carrier, charge carriers, and then the photo-generated carrier will separate it by the PN junction and use the electrode, front electrode and back electrode. We will transport them to the load to do electrical work. So to describe the solar cell, we have equivalent circuit model, which will not only the current is generated, also the shunt resistance and the series resistance, it comes from our structure. So this one, use this model, we can calculate the relationship between current and the voltage goes through this node when the solar cell works, do functions. this is a realistic solar cell. So most important and basic features is the current voltage curve. So the black one will give you a curve about on the dark, means no photons into this solar cell. The red one means, okay, let's shine light on the solar cell and what it looks like. So the solar cell give you electricity and voltage drop or voltage potential. So what we want is do electric work. We want power. So power is current times voltage. So if we plot the voltage versus power, so it will give us a curve, means the output power it can give if our node is a different condition. So from this curve, we can see, okay, at one point, we have maximum power output from this solar cell. We want this solar cell work at this condition. So this point is what we want. So how to characterize it? It's harder to extract. It's not a direct way. So it corresponds in this point, the J, the current, and this voltage. So the area J times V is the power we want. And we can easily abstract the GSC. So this point is ISC or GSC. So this point is VOC. So this rectangle area means a larger power, right? So if we use the ratio of this maximum working point rectangle to this ISC times VOC, this ratio is a fill factor. We want this as high as possible. So if we, what we want is this one, P max power. So we can use ISC, VOC, and the fill factor. This times together is the output of power we can get. So efficiency means the output of power we can get over the input power we put into the solar cell. So it means we have 1 kilowatts per centimeter, per meter square, then we can output, if with 20%, it means 200 watts it can give us. So the key parameter for solar cell is ISC, VOC, and fill factor. So let's take a look at what is ISC, how to calculate ISC, what's the maximum value it can give us. As we say, about band gap, we can convert these photons. If we can do an up limit, it means one photon, 1 electron, whole pairs. So we can do an integrate the photon flux with the photon energy larger than band gap, then it can give us this code. So this is the maximum photocurrent we can get. So we can calculate in this way, but in reality, not all the above band gap can be converted into our useful electrons. So some above band gap, I mean, for example, this is a reality response for silicon solar cell. The band gap is the limit is at 1100, between 1200. So above band gap, it's not 100% convert into electricity. It's below. So why this happens? It's because some recombination, and for example, this region have some region, and this one due to reflection and some bulk recombination. And the front, the high energy have less absorption depths. Also, it will recombine at the front surface. So we have a thin layer of TCO, transparent oxide right? So that also will absorb the photons. So the RSC can be calculated use this formula if we this called EQE, external quantum efficiency. So this will give us all the photocurrent we can get. In we want to reduce such loss. For example, we deposit anti-reflection coating, ARC. It means reduce the reflection. If we have a smooth surface, the reflection is a lot. It cannot go into the solar cell and become electricity. Also, we want to increase the optical path by light trapping. It means sometimes we have some thin layer. It cannot absorb 100% of the photons. So we want to reflect it and then we absorb something like this. So we want the light go into our solar cell and then convert by it. So the photovoltaic, the generation of photovoltaics, the key point is, so we have multi-wavelengths of photons and excite the electron. It will relaxation to the bottom of the conduction band and this one. But how to describe the behavior of electrons and holes in a material? We use Fermi level. Under illumination, we have quasi-Fermi level, different of it. We call the Fermi level splitting. Why this is important? Because when we shine light on the solar cell, the photo-generated carrier will transport to the holes will transport to n-type, and the electrons will transport to the n-type, and the holes transport to this one and conducted by and then extract by the electrode. So the Fermi level, the energy level or chemical potential of holes and electrons is a differential of the quasi-Fermi level. This one is related to the excess carrier, especially the minority carrier. So we use the VOC we can get first is proportion to the band gap, higher band gap, higher VOC. But for the same material, the band of the material will reflect by the excess carrier density, or we can call it a minority lifetime. This can be measured and reflect the process happen in our solar cell. So this map tell us the potential we can reach. So some silicon, some material we have, we can reach 18% of current potential, but the voltage and the field factor potential it's less than some good solar cell. We have 19%, but most of the solar cell is 17%, even 14.5%. Group 5 doping in cadmium telluride, which increased the minority lifetime a lot. So the recent efficiency improvement can reflect by this one. So it provides how do we optimize the solar cell. For field factor, it's affected by series resistance and shunt resistance. Typically, for this IV curve we have, so this one, if this one is as parallel as much to the horizontal line, it's very good. If we reduce the shunt resistance, it means also the series resistance is if we want this slope at this point as vertical as possible, otherwise it's not good. So some material it's very easy to achieve, but for the shunt resistance, for example, if we have some conductive phases in the absorber all have some voids in the absorber. It will connect the front electrode and back electrode together directly, so it will leaking. It means leaking. For serious resistance, we want only contact electrode with the absorber, but some material there is not an ideal contact. The back contact is most of the case it's like a Schottky contact, so this will increases and decrease the field factor, thus the efficiency. So we have review the ISC, VOC, and the field factor. So let's look at some specific case for the material. The most fundamental one is the silicon, is the first generation we call, and the second generation is the C-film and some OPV and some highlight perovskites. The third generation is designed for enhance the efficiency further. This is a typical, very early stage silicon solar cell. So as we see, we need a P-type, N-type material, which will as a junction, and we want the absorber to absorb the light fully. Sometimes it will not. So we need to do some designment. So for this solar cell, what loss it can have? So we have electrode and the front. So this the light will not penetrate into absorber. It's not transparent to light. So the area we have, the much more area we have, the more loss of current we will have. It's equal to reflection, and the interface always means high recombination. It will lose both IC and GSC. Also, the back metal absorption, a lot of it. The bulk recombination means the quality of the material. So it gives us just less than 15%. For silicon, the light scattering and trapping is very important because it's the initial is a wafer. Wafer is a very smooth surface. Very smooth surface means reflection, and the absorption coefficient is low, is with higher, and some will transparent trait. So we need a back contact to reflect, and some texture to reflect the light, to trapping the light into the absorber. So that's why we need this texture, and also the anti-reflection nail. This one do some improvement. So we put the electrode from front go to back, so it will not shed light. And it's also reduce the bulk generation, means the quality of this wafer improved. And the passivating silicon dioxide nail means passivating nail reduce recombination. Something like this. So pn-junction is at the back side. I want to introduce this one, PERC silicon technique. It's a concept proposed in very early stage, 1980s, Martin Green in Australia. It's about to use the point contact at the back side, because the back contact, the interface, the area interface, the more you have, the more loss of current you have. So we use the whole back contact with some point contact. So this one, why I want to say, because 5 years ago when I was at a company do internship, the industry are considering, should we adopt this technology or not? Because if we, this is a general structure they have. If we want to use this concept, we need do some patterning on the back contact. It means we need at least 2 additional steps to fabricate it. It will increase in cost, but it will also increase the efficiency. There is a balance, the efficiency improvement and the cost you add additional step. So finally, most of the company, this is a dominant technique right now, and most, especially for mono crystal silicon, they have a higher efficiency improvement. And now we have 20% or 21% solar cell module, but currently we will experience lacks technique. We want to further efficiency improvement to reduce our cost or something like this. It's interesting. So second is about C-film solar cell. C-film solar cell, the key point is the absorption coefficient. So for silicon is an indirect band gap. It means absorption coefficient is low. So it takes about 200 microns to absorb the light intensity. But for C-film material, its direct band gap, it means absorption coefficient is high. We just need 1 to 4 or 1 to 5 micrometers to absorb the same amount of light. It means, okay, we can reduce the thickness of the PV module. This is a demonstration. So it depends on different kind of material. So for C-film, the cadmium telluride, CIGS, they all benefit for this. We, if C-film PV want to compete with silicon, they will experience a shortage of material. If in terawatt, now silicon is gigawatt, 500 gigawatt. If we install 500 gigawatt of cadmium telluride and CIGS, we don't have that much material. So this is about abundance in our Earth. So for silicon, they also have some concerns about shortage because they use silver paste. The more you installed, the more installed in the PV, the less we can use for other uses. For CIGS, we have indium. For cadmium telluride, we have tellurine. So that's could be a potential concern, especially in next 10 years if the solar percentage is 10% for the whole electricity production. So for this console, we want to use ultra thin absorbers, means to further reduce the thickness of the absorber, but try to achieve or not to reduce efficiency too much, or use some new materials, means okay, some abundant material to solve this problem. So technique always proceed with different way. Also, they might a way to recycling the PV modules for some materials, because the lifetime of the PV is 25 years. After 25 years, the efficiency is low, and we need to recycle it, maybe also solve some of this problem. So this is a cadmium telluride plant in, well, somewhere. Okay, so cadmium telluride is mainly produced by First Solar in USA. CIGS is mostly produced by a Japan company, and there are 2 in China. They brought some company in USA and Germany. They also began to produce CIGS modules. For gallium arsenide, we call it it's the princess of solar cell because it's very expensive, but the performance is pretty good. So we can also use it to produce electricity for our lifetime, for our daily lifetime. But this is useful for space application. We don't care about cost. We want to power some device in the space. So we want the weight reduced and as higher efficiency as we could to do it. So a lot of efforts have been made for this kind of solar cell. Next is OPV, organic photovoltaic. Organic photovoltaic is due to its we can design it with lots of modification, and the processing temperature is also low, so they have a lot of advantage. In the past 15 years, the efficiency is not high, but recently, the highest efficiency increased to 17.5. So it's exciting for some OPV guys. They make it. So the organic material, there are lots of conduction band or valence band. There are some also there are some orbits can transport carriers, but it looks like this. The semiconductor is a junction, planetary junction for OPV. They use different kind of material, and the electron always go to low potential. The holes always go to high potential. That's the driving force they can separate. And they can make some bulk junction. You see the this donor and acceptor can have as much as a surface as it can to transport the electricity. Is advantage over semiconductor pn-junction. Next, I will say this material, perovskite. It's how much time? Okay, I should less time. Okay, let's go faster. For perovskite, it's a new star. So you see, this is the efficiency curve. It's less than 10 years. It achieves to as high as cadmium telluride and CIGS, and the principle to how to work, it looks like OPV, but it has some excellent variety lifetime. The early concept is its stability, and the sustainability means they use some lead elements and some other. There are a lot of small company began to, they put efforts to commercialize this material. Let's see what will happen. There are some application cases that we want a lightweight substrate. Lightweight substrate, the metaphor is lightweight, but the most lightweight is some polymer. Some polymer, you see plastic in your lifetime, you buy in market. It's very lightweight, but for the C-film PV, it cannot deposit on it because the processing temperature is pretty high, it's already melt. But for the perovskite and OPV, they have low temperature deposition process. They can do such applications. It's also attractive. Okay, next, so we go to how to enhance the junction efficiency. The single junction efficiency is only 13.3%. If we want more output power, we need to use one technique is multi-junction solar cell. We use different band gap material to absorb different range of photons, then the total efficiency will increase. And if do some concentrator, this is a concept to utilize the spectral irradiation. This example use different band gap. They have different response than the total the current and the efficiency will increase. This is for gallium arsenide. They can do some component engineering. They can deposit layer by layer what we want to put on this, and we can design this structure. So it's for multi-junction solar cell gallium arsenide. It's not it's hard to do for cadmium telluride and CRGS because the deposition technique is different. Next is some advanced engineering. So solar cell deal with the light and we absorb it and separate it. So assumption is one photon generates one electron hole pairs, so convert one electron. But we want one photon to generate more. So this is possible for some material. So if I have for example, my material band gap is 1 eV, and we have some, no, this material is not good. So let's use this material. So the band gap is 0.72, and it can give you 1.5, 1.4 electrons. It means for these photons, the energy is far exceed the band gap. When the relaxation, the additional energy will give to other photons to excite it. So this is deals with the absorption process. One photons generate more than 2 or more electron hole pairs. This one deals with the area of the junction. So for semiconductor pn-junction, they are plain junction. If the substrate area is fixed, they are just limited junction. But for this one, the side wall will give you a lot of junction, and you will enhance the harvest of light. Yeah. This is a concentrator PV. It might not suitable put here, but it's about how we further improve the efficiency. If we cannot change the solar cell, we can change the light. We can concentrate the intensity by some optical lens. So it can also give you higher efficiency for this solar cell. Okay, all in all, so the solar cell PV is, the cost is reducing currently. So we can, it's still, I think it's still expensive than the electricity from hydrogen or coal, some other electricity cost, but it will reduce, and it's a strategy for energy because lot of consideration. And the solar cell requires absorption, separation, and collection. That's the basic process it has. Lots of material have been developed or has been, we are also currently investigating them. So every material has its advantage and disadvantage. There is no perfect material for PV. I think it depends on the application you want. And the people are looking for even higher to, but this technique is at lab scale. It's the industry don't like it because it cannot produce money. So it's good for PhD students and research. Yeah, that's it. So thanks.
Great. Thank you, Rujun, for a very comprehensive overview. let's see, we have plenty of time for questions. So let me first
Yeah.
open it up to the students. Let me actually ask a question. I guess, can you talk a little bit about your specific research area? So what are you actually performing research on?
Okay. So what I am doing is CCTS solar cell. It's a copper, zinc, tin, sulfide, very similar material with CIGS. So the concept is about the abundance, means if CIGS or cadmium telluride in large scale. So for this material is a 4-component material. So there are a lot of challenges on fabrication. If we want to put 4 components together and give a good pure material and the desired electricity property we want, it's challenging. So we have do a lot of efforts to sell. Yeah, so we use different techniques, different people. That's it.
Are there companies that are commercializing this material?
Not yet. The highest efficiency for CCTS is only 12.6, is still lower than CIGS and cadmium telluride.
Okay, sounds good. I should point out, Rujun talked about some of the multi-junction cells that we will talk about later in this semester. So, and of course, Rujun also talked about light trapping, which we talked about a few weeks ago. So hopefully the students, you're able to connect it to more realistic problems. What we talked about was more idealized. I guess let me ask you, are there any questions? I don't want to hog the questions. I don't see any. Feel free to talk. Okay, I have one more question. So we have this, we have seen this huge prevalence of silicon essentially because of the reduction in cost. In your opinion, I assume you've been following the industry. Is this something that's reaching a saturation, or is it continuing in terms of price per watt, I suppose, or installed price? Do you have a
PV?
I mean, right. I mean, do you think in the near term silicon will still dominate? And what do you think? 5 years, 10 years?
I think it will still dominate because this technique is very mature. It's for CIGS, for example, not only the shortage, but also the, for example, if you produce 100 pieces of solar cell, if 19% of the pieces works, then it's good. So the process window for CIGS might narrow. I think that's why one of the reasons the cost is high for CIGS.
Right, I see. Did you, maybe I missed it, but did you talk about perovskites at all?
Yeah.
What is your opinion on these materials?
I don't know. I mean, people are crazy about it. We can use crazy. In the stability, I mean, the solar cell needed to work for 25 years. Even there's some improvement in the scientific paper says, okay, if we accelerate it, some kind of condition, it can stand I keep an eye on it. I don't know. I mean,
Okay.
if it come to commercial, it will be really good.
Yeah.
Some material is also expensive. Some whole extract a whole nail, something like this. But they will have a lot of policy to support them, I think, if they have potential.
Right, right. I think in an industry like solar, you have to really consider not just the novelty and lab scale demonstrations, but also very, very large scale up, because otherwise you don't make a difference. So in manufacturing, as well as the other things have to be considered. So great. Are there any other questions? Oh, I hear something. Okay, maybe not. Well, if there are none, but thank you, Rujun. This is a fantastic overview. I really appreciate it. And if the students you have any questions, feel free to email me. I'm happy to relay them on to Rujun and get the answers. Great, so we'll end a little early today, and I just wanted to also point out that I made an announcement for the class on Thursday, so make sure you guys take a look at it on Canvas. And if you have any questions, again, post on Slack. Thank you very much. Thank you, Rujun. Take care, everybody. See you on Thursday.
Thank you.
Thanks, everyone.